Hi, this is naturalist wildman Steve Brill. You're watching Foraging with a Wildman, part of the Inquiring Naturalist series. We take a look at the positive sides of the environment, natural history, ecology. I am an expert in edible wild plants and have been trying to learn as much about all areas of science and the environment as possible. And I'm going to share something that's been close to my heart since I was a little kid, which is dinosaurs. We are going to be talking dinosaurs today, and my special guest is Brett Bennington, paleontologist of Hofstra University. Hi, Brett, how are you?
Hi, Steve. How are you?
Very good and very excited. I've never really had my hands on dinosaur fossils before. And
Well, here you go.
yeah, and we have some children's toys, which you told me are actually very good models of the dinosaurs.
Yes, these are replicas that are sold by some of the major museums. Most of the animals here, or most of the dinosaurs represented, are British Museum replicas. They've been around for a long time, and they're accurate scale models of the animals, reconstructed to the best ability of the curators of the museum. You might quibble a little bit with how much meat is padded out on the thighs of the animal.
I don't like that the tails drag on the ground.
The tails drag on the ground, which they probably didn't, but you can't get the model to stand up straight unless you have the tail dragging on the ground. For most purposes, though, they're very accurate.
Okay, well, we'll use them to illustrate some examples of what the dinosaurs were like and what some of the different groups were like. First of all, I want to find out a little bit about you.
Okay.
You're a paleontologist.
Yes.
What do you do at Hofstra? What do you do out in the field? How did you get involved with dinosaurs?
Well, I'm what you call an invertebrate paleontologist. Right, I'm spineless. There's a popular T-shirt that says some of my best friends are spineless. So I deal mostly with sea creatures, clams, oysters, snails, animals like that.
Oh, why not land invertebrates?
Well, it's not really my specialty by training. My primary interest is in looking at and reconstructing and interpreting ancient marine ecosystems. But I'm very interested in dinosaurs. I read up on dinosaurs. I read the latest material that comes out of the profession on dinosaurs, and I've done some work with land animals, but much older ones than the dinosaurs.
Mm-hmm.
So it's like yourself. It's always been dinosaurs have always been a great fascination with me.
Okay, well, let's start with pre-dinosaurs. One of your discoveries. Who is this guy or gal?
Well, this is an anthracosaur. This is
looks sort of like a reptile or maybe an amphibian. Is it a very primitive reptile or a reptile-like amphibian?
Well, it's most likely an advanced amphibian. This animal.
How would you tell it was an amphibian rather than a reptile?
Well,
unless you caught it laying eggs on land or
what
water.
You have to do is you have to look at the different bones in the skeleton. This is a reconstruction based on some skeletal material that was excavated in West Virginia, not by myself, by a vertebrate paleontologist. And there are certain features in the skeleton of amphibians that are shared by all amphibians. So if you find...
What are some of the features? Is something we can see here?
Well, there are bones in the head. They're not very well shown on this reconstruction, but just some peculiarities in the shape of some of the bones and some of the openings in different bones. These are not features that are important for the survival of the animal. They're sort of accidental features in the skeleton that get passed on as these groups evolve. Mm-hmm. So if you're part of one family of animals, you keep inheriting these little peculiarities of your skeleton. And then when a paleontologist comes along and looks at your bones, if he or she finds one of these peculiarities, then he or she can pigeonhole you and say, you were an amphibian. You have a funny little hole in the back of your skull in a certain place.
Okay, and what is the fossil that relates to the anthracosaur that you have
my interest
here?
in the anthracosaur comes from some work that I've done out in West Virginia with footprints. Let me reorient this for you a little bit. Like that, and if you can get it so that the light is coming down from the side, you can see them a little better. What we have here are 3 toe marks, 1, 2, 3, and then 3 other toe marks behind the front 3. And this is the back foot and the front foot. This is a piece from an exposure of rock along the highway where we found extensive series of these footprint pairs. We find entire trackways where you'll have 2 footprints and then 2 more and then 2 more and 2 more, and sometimes going on for 11 or 12 pairs of trackways.
And where did you find this?
This is out in West Virginia, near the Virginia border.
And you were just walking around there? You knew that there were fossils?
Well, it's a nice exposure of rock, and it's a place where we take students. When I was a graduate student down there, we always took students out to this area to look at this wonderful sequence of well-exposed rock. And in part of the sequence, we find these very fine-grained siltstones, which break into nice flat pieces. And for years, people have been finding footprints.
How was the siltstone formed? Just from deposits of silt in a river?
Yeah, we think that these layers of silt were deposited upstream from a river that was emptying out into the sea. This was a time back 300 million years ago or so when there was a huge shallow inland sea covering a great deal of the interior of North America, and the shoreline of the sea was about where the West Virginia border is today. But the ocean, instead of being to the east at that time, was to the west. To the east was an eroding mountain range, and it would only be after you'd crossed those mountains traveling east, you would have stumbled across Africa, which was starting to. There was probably a little bit of Atlantic Ocean left, but then Africa was very close, and it was coming in to collide with North America a little while later and raise the ancient Appalachian mountain chain.
Okay, and what did you learn from these footprints?
Well, from having a lot of different specimens of the footprints, some of them much better impressed than these. I didn't bring the best example of footprints we have because those are in a museum, and they're not generally allowed out unless they're being studied by another specialist, because they're the best example of the fossil, what we call the holotype. So they're kind of jealously guarded. From the arrangement of toes, the number of toes, the different lengths of the toes, we were able to figure out that the animal that made the footprint was most likely our friend the Anthracosaur here. It's an animal that we know from skeletons was alive at that time, and its size and the morphology, the shape of its toes on its foot, were a pretty close match for our footprints. And with footprints, you can never be exactly sure exactly what the animal was that made the footprints, but you can try and come close to the general group of animals. And this is the best candidate for the track maker.
Okay, well, let's start talking about the dinosaurs. How long after the Anthracosaur did the dinosaurs start emerging?
Well, let's see. Roughly 100 million years later. The Anthracosaur, well, let's see. When did dinosaurs appear? 135 million years ago. Mm-hmm. I'm very bad with numbers. Help me out here if you can.
Yeah, that's about it.
So about 100 million years later.
And what was the Earth like at the time that the dinosaurs emerged? What else was around in terms of animals and plants?
Well, the Earth, when the dinosaurs first appeared, the Earth was a lot different than it is today. If you were arriving from outer space, from another planet, and you went into orbit around the Earth, you would have noticed one very, very large continent, kind of smack right over the equator, and then a huge ocean on the other side of the Earth. In the what we call the Triassic period, when the dinosaurs first appear, all of the continents had drifted together and collided and assembled into one big supercontinent, which we've given the name to Pangaea.
And the geologists are still wondering, with all these continents moving in different directions, why they all happen to congeal into one place, and apparently that happened more than once.
Yeah, well, it's probably just a function of the Earth is a globe, and it's only so big, and as the continents are sliding and drifting around, just by chance, every now and then they're all going to kind of bunch up together and sort of form a logjam.
But they don't all bunch up together where one just happens to miss. They either bunch up together with all of them, or they drift apart.
Well, there's been a whole series of collisions and different pieces of continents coming together and then moving apart again. So it's difficult to say if there's any sort of pattern to the continents coming together in one large landmass. We think it's happened twice.
Right.
It may have happened again much, much farther back in history than we really have a lot of rock evidence left to look at. So
Okay.
the further back in time you go, the more difficult it is to figure out what happened, because the evidence for what happened gets harder and harder to find.
Right. Okay, getting back to our early dinosaurs, what kind of advantage did they have? Why did they rise to become the dominant creatures of the Earth, and what were they competing with?
Good question. Nobody really knows why they became so successful. We have some ideas.
What are their strong points compared to other animals? I mean, human beings have brains, birds can fly. Why is it good to be a dinosaur?
Let's go back to let's go sort of imagine that we've gone back to the Triassic 130, 140 million years ago. What would we see back then? Well, we wouldn't see many dinosaurs. When dinosaurs first appear, they're not a very important part of the animal faunas that are around. There are lots of other reptiles. Some of them very, very large, larger than the rather small dinosaurs.
I know there was one crocodilian that was the size of a bus.
Yeah, there were these animals called Rorasicians or Rorasuchians that were sort of crocodile-like. They were kind of supercharged crocodiles that got to be.
And they lived on the land, not
yeah, and they
in the
lived
water.
on the land. Yeah, when crocodiles are interesting because when they first evolved, they're not water-dwelling animals. They're two-legged bipedal animals. So your earliest crocodiles would have looked like, sort of like reptilian kangaroos that weren't hopping but were kind of scurrying around on two legs. But so you had these sorts of early crocodiles. You had these large reptiles, which are broadly called thecodonts. Some of them were very, very big carnivores. You had all kinds of these very strange-looking plant-eating reptiles that were not dinosaurs, but were other groups of reptiles that were sort of filling the ecological roles.
Okay, and what were tell us about the mammal-like reptiles.
There were some mammal-like reptiles still around.
These are our ancestors,
These
apparently?
are our ancestors. Mm-hmm. These are the ancient descendants of the mammal family, and the current thinking.
The ancient ancestors.
Oh, right. Thank you. The ancient ancestors. The current thinking on this is that very early in the evolution of land animals, the mammal line and the reptile line split and formed two distinct groups: the synapsids and the diapsids.
Has that been verified by genetic or DNA testing to see how far apart reptiles and mammals were?
Well,
is there any kind of DNA clock?
Mammals are definitely a separate group from all the other reptiles.
How did they separate? Like right after the two evolved from amphibians, or quite a bit later?
The evidence on that is sort of equivocal right now. It's this radiation. The divergence of mammals and reptiles, and then the radiation of all the different reptile groups happened over a reasonably short length of time. Geologically, and it's difficult using these sorts of protein and DNA analyses to pin down the timing of events.
They're too close together.
They're a little
too
too
far
close
back.
together and a little too far back. Yeah. So
far.
Yeah. So for now, the biochemical evidence for when these lineages split is not really conclusive, but as far as I can tell from the reading that I've done, the general consensus emerging among zoologists is that the split occurred very, very early, maybe sometime back in the early Permian or in the Pennsylvanian, back maybe 250 to 300 million years ago. And once these two lines diverged, that was it. They were forever separate. And in the period of time before the beginning of the age of dinosaurs, before the Triassic time called the Permian, the mammal branch of life radiated into all kinds of different forms, and they the early mammals kind of took over the world. And traditionally, we've called these animals mammal-like reptiles.
Okay,
but maybe that's a misnomer, because they might not be related to reptiles at all if the division between reptiles and mammals happened along very, very long time ago, then there's really no point in calling these animals reptiles. We should just call them early mammals. But that's just a semantic argument.
Okay, but then again, mammals, probably true mammals, came from maybe one very narrow lineage of all of these diverse forms, because there was something called the Permian extinction,
Yeah. Mm-hmm.
which makes the Cretaceous extinction look like a picnic.
Well, for marine life, it does. Yeah, you had in the Permian, you had all these mammal-like reptiles radiating all these very, very weird forms and filling lots of different niches in the ecosystems. You had large herbivorous mammal-like reptiles and predatory mammal-like reptiles. And at the end of the Permian, there was a big extinction, but it didn't actually affect land animals that much.
Really,
it wasn't
was more
a big deal.
sea animals. What I had read is that it devastated way more than the Cretaceous extinction did.
In the oceans, marine life at the end of the Permian was cut back. David Raup at the University of Chicago has estimated more than 90% of all the species of marine animals that were alive on the Earth went extinct.
And how many percent went extinct at the time the dinosaurs went extinct?
I think, I'm trying to, for species, I think the estimates go as high as 70%. Usually it's expressed in terms of families of animals, a little higher up.
Okay, how many families in the two different extinctions? I want to get sort of a feel for how much worse the earlier, less popularized extinction was than the later one, just roughly.
Roughly, I think about maybe on the level of families, about 70%. And when I go back to my office and look up the numbers, I'm going to realize
we'll do another show.
But let's say 70% in the Permian and maybe down to 40% in the Cretaceous.
Okay, anyway, the Permian wiped out a lot of the early relatives of the mammals.
Yeah,
you still had some of them left. You had dinosaurs, you had crocodilians, and you had other groups of reptiles, and the dinosaurs came to dominate the Earth. What are the theories? I know no one really knows, but what are some of the theories of why the dinosaurs did better than everything else?
Well, I think there's roughly two theories. There's the theory that says that the dinosaurs were better built than these other animals. The first dinosaurs were bipedal, two-legged animals. They were upright. They walked with their legs underneath them. They weren't sprawling and walking like this. They had their legs beneath them, walking erect.
What about the mammal-like reptiles? Didn't they have the legs underneath them, but they were four-legged?
They were sort of halfway. And some of them were moving towards being, fully erect. Some of them were sort of semi-erect.
So the dinosaurs are probably faster predators, and maybe the herbivores could get away faster.
Yeah, one line of thinking.
Are there other lines of thinking?
Well, the other line of thinking is that they just got lucky. That happenstance. That at the end of the Triassic, there were extinctions all around the ecosystem. The dinosaur species that were around, most of them went extinct. These mammal-like reptiles, most of them went extinct. Lots of the crocodilian-type animals and all these other different reptile groups that were around, they went extinct. And that the dinosaurs may have just been lucky. That enough different species of dinosaurs may have been left as the Jurassic began, the early Jurassic, that they had first dibs on the available ecospace.
So it's like you reset the chessboard, and this time the dinosaurs made the best move for the first move. Exactly.
It's like I've been in sailboat races where I'm in a sailboat that's way out ahead of everybody else, and then the wind dies, and everything bunches up, all the sailboats come together, and then it's a whole new race.
So there's no determinism. There's a lot of contingency, as well as the laws of nature working themselves out.
Right. That's a big question in the study of extinctions and the study of evolution.
Or just the study of science. How much is determined and predictable, and how much just
happens by chance.
Yeah, that deals with history more than laws of nature.
Exactly.
Okay, let's look at some of the different groups of dinosaurs. We've got a lot here. Why don't you tell us about the different groups, why they evolved these different forms, what their specialties were?
Okay, well,
what was the biggest group? I guess herbivores. No, in terms of how many species. I guess herbivores are always more common than predators.
Yes, that's
with any group in any age. Obviously, if there's as many herbivores as predators, the herbivores would get eaten, the predators would starve.
Starving predators, yeah. And there's an interesting ongoing argument there with dinosaurs. And one of the ways to try and figure out if dinosaurs were warm-blooded or not is to look at the ratio of predators to prey.
Right.
Cold-blooded animals don't have to eat as much as warm-blooded animals, so in an ecosystem you can have more predators relative to the number of prey because the predators aren't eating as much.
Well,
With warm-blooded
do
animals,
the fossils fossilize in equal quantities?
well, that's
and you've got to
that's
die along a riverbank to be buried in sediments and fossilize.
well, that's those who argue that the ratio of predators to prey in dinosaurs suggests they're warm-blooded are countered by other paleontologists who say your data is not good enough. You don't know if the information you're getting is biased because in general you seem to find more fossil plant eaters, fossil herbivores, and you find fossil predators, with some exceptions. So,
well, what would the fossil evidence of mammals show? Are they warm-blooded or cold-blooded, according to the proportions of mammals we have now and looking at fossils of maybe earlier mammals?
The principal proponent of warm-blooded dinosaurs is Dr. Robert Bacher. Wears a hat something like this, a big beard, a very, very charismatic, very dynamic man. And what he's tried to do is look at fossil faunas of mammals from after the dinosaurs and count predators and prey and look at predator-prey ratios in fossil dinosaurs and then go back before the dinosaurs, back to the Permian, and look at some of these early mammal-like animals, which he suspects maybe are far enough back in the mammal line that they hadn't become warm-blooded yet.
But that's not really known either.
But his predator-prey ratios come out showing that there seem to be, for these early mammal animals back in the Permian, they have relatively high numbers of predators relative to prey, whereas the dinosaurs seem to have predator-prey ratios that are more like the later mammal faunas. So he argues that this is a good piece of circumstantial evidence for dinosaurs being warm-blooded. But anyway, let's get back to the different dinosaur groups.
Dinosaurs. Why do they divide into these groups that are represented by these models?
Well, let's rearrange our models a little bit. We have the large long-necked dinosaurs together, and then we have our two representatives of predatory dinosaurs. And these belong with the long necks for a reason that I'll talk about in a second. And then the rest of these animals we can put over by themselves. Now,
so are these the three main groups of dinosaurs?
Well, you start actually with a two-part division.
Two-part. Okay, so we divide them down this way.
Right.
Okay, and what are and this of course means that these all evolved from a common ancestor, or they split from one common ancestor that gave rise to then three more splits, and that gave rise here to one group and the other group, and then again subdivided until you get to all the species.
Right, exactly. And as far as we can tell, most of these splits had occurred back in the late Triassic, at the beginning of the age of dinosaurs. These dinosaurs here all have a hip.
We're talking about these four.
This group, these four here, they all have a hip structure that looks somewhat like modern lizards have. They're not related to modern lizards, but the general design of the hip bones is reminiscent of modern lizards.
Okay.
These dinosaurs here have a hip structure which is reminiscent of modern birds. And the irony of that is...
Didn't modern birds come from this group?
That's sort of the irony of this division, is that modern birds evolved from the lizard-hipped. We have the lizard-hipped dinosaurs, the bird-hipped dinosaurs. And modern birds seem to have evolved from the lizard-hipped dinosaurs. But again, lizard-hipped and bird-hipped, we're not using these terms in a strict genealogical sense. It's just that's what the hip looks like in these animals, in a very general sense. And this commonality of hip structure unites these two groups as having a common ancestor that diverged. That these groups diverged later than the common ancestor of these together.
So looking at the lizard hip ones, then the division between these two groups is pretty obvious, because these went the path of predators and these went the path of herbivores.
Yeah, in a sense, this group here retained the ancestral way of life of the dinosaurs. The earliest dinosaurs were predators, as far as we can tell. And then some of these early dinosaurs specialized and started getting very large and became sort of the elephants of the dinosaurian world. And they're most obvious feature is they have long necks.
Right. Okay.
And
So
that's
you have Apatosaurus, formerly Brontosaurus, and you've got Brachiosaurus.
Brachiosaurus, right?
Okay. And this was like 6 stories tall or something.
Yeah. Huge.
Okay. You could look into my bedroom window, but not
Right.
be smart enough to see what I was doing.
We call these are the sauropod dinosaurs, and these are the theropod dinosaurs. Sauropod means lizard foot, theropod means beast foot. The names are not that significant for telling you about the animals. The reason for having long necks in this group of dinosaurs was debated for many, many years, and it was thought for a long time, up through most of the 20th century, that these huge, ponderous, overbearing, overweight animals lived in the water, that they couldn't possibly hold up their enormous bulk without floating around in the water, and that they were using their necks as snorkels with their heads out on the surface and their bodies below.
Well, there have been some footprints found in the water.
In water, but probably shallow water, and it's not unusual for animals to walk around on the edge of bodies of water. It was in the 60s and the 70s that people started analyzing this idea, and it was realized very quickly that these animals couldn't possibly live in the water. They have.
So how do we know that they're basically terrestrial and not aquatic animals?
Several reasons. They have feet which are designed remarkably like the feet of elephants.
Yeah, these do look like elephant feet.
They have very, very sort of blunt, tree trunk-like feet.
Anything this big would have to have these kinds of feet. Don't rhinoceroses have similar feet, and they're not as big as elephants?
Right. I don't really know offhand what the foot of a rhinoceros looks like. I know they're similar. They're very similar to elephant feet. The toe bones are almost vertical, so the bones are arranged to carry a tremendous amount of weight. And if an animal that had they have relatively small feet in relation to their huge bulk. I mean, if an animal like this tried to walk at the bottom of a lake, it would probably sink in and have trouble moving. So you look at the structure of the feet, and you see that the structure of the feet looks like the feet on animals that walk around on dry land, like elephants.
Okay, what other evidence?
Well, you can also do some simple physics calculations, and you discover that if our friend Brachiosaurus here was walking at the bottom of a lake and his head was above the level of the lake, then his lungs would have been down 40, 50 feet beneath the surface of the water. So his nose would be breathing air at atmospheric pressure, and his lungs would be trying to expand with atmospheric pressure against the water pressure of 40 or 50 feet.
He better swim and keep his body close to the surface, or he'll
Right. If he was standing
drown.
on the bottom, his lungs would collapse.
Or I know there's been footprints where some of the sauropods you see like 2 feet.
Okay, those are interesting footprints. What they were finding with these are famous footprints from I believe Texas, where they were only finding the front footprints from a large long-necked dinosaur. No sign of any back footprints.
So they were probably in shallow water, sort of paddling along a little bit.
That was what was thought. But those footprints have been reinterpreted, and the current thinking is that what we're seeing with those particular footprints are not the actual footprints themselves, but what are called underprints. So say you have several layers of mud built up, and you put your foot down in the mud. Your foot makes a depression in the top layer of mud, and that depression in the top layer pushes down into the layer beneath, which then pushes down into the layer beneath. So if you look at the top layer, you have a nice, beautifully formed footprint. If you peel that layer off, the next layer will also show a less well-formed footprint. And then if you peel that layer off, the third layer would also show an even less well-preserved footprint.
And that's what we've found.
It's thought that these footprints, these trackways that just have the front feet of these large long-necked animals are underprints. And because when the animal is taking a step, it's sort of throwing its weight into its front foot. It's not at all uncommon for the front footprints to be a little deeper and a little better
So
impressed.
there might have been hind footprints there too, which we didn't see.
Right, exactly.
So then the body was still pretty horizontal, and it might have been shallow water.
Exactly.
I don't know what it could possibly do submerged in the water anyway. With this long neck, it couldn't really reach very much.
Well, another aspect of this is that it was traditionally thought that these animals fed on aquatic vegetation, which is generally soft and not. Or at least back in the Mesozoic, was fairly soft and not too tough to eat. But if you look at the teeth that these long-necked dinosaurs had, they had teeth that show a pretty good amount of wear, and they were teeth designed for cutting and cropping and stripping pretty tough vegetation.
Well, the Mesozoic was a pretty warm period with a tremendous amount of vegetation. There would have to be herbivores evolved for taking advantage of the land vegetation, and there's really no other candidate but the herbivorous dinosaurs for that. You can't let all that plant material go to waste. I wasn't around to eat it then.
Right. What kind of plants were around back in the Mesozoic?
What kind of plants? You had a lot of pines, you had fern trees, you had cycads. Nothing that we could really eat.
No, these are tough plants.
Yeah, we would have
hard to deal with.
We would have starved because we need the flowering plants to have food. Except for maybe hunting, we would have had a very difficult life if we were around. And we could eat ginkgo nuts; those are still around today, and the dinosaurs probably ate them. But
and if you look at the teeth of these long-necked dinosaurs, they seem to be teeth that were adapted for eating these tough types of vegetation that were around on the land at this time.
Okay, well, maybe there's something that would help them with these tough vegetations. Why don't you tell us about our gastroliths here? Tell us what a gastrolith is. People in the audience, if you have indigestion, if you have trouble with your food, try a gastrolith. What would we do with them?
Well,
we'd swallow them?
A number of different animals that are alive today will swallow stones to help them digest, and it appears that...
don't try this at home yourself.
Yeah, do not try this at home. I don't want to be the subject of a lawsuit. I told somebody to swallow rocks. With some skeletons of these large long-necked dinosaurs, the sauropods, we find associated back where the stomach would have been piles of these polished stones.
About how many in the larger herbivores?
You're talking 50 to 100 stones.
Really? So you see a big pile of these polished stones.
It's not. They're not that common. There aren't that many specimens.
About how many?
Found. Offhand, I couldn't tell you. But
we've got some in our hands, so they couldn't be that rare, or they wouldn't have let them into the QPTV studios.
Well, that's sort of an interesting thing. Is that you find a lot of polished stones in rock formations that you really don't expect to have polished stones that are dinosaur age. And some people think that they periodically just regurgitated their supply of rocks and then went and got new ones. Perhaps after a while the rocks would get so polished and worn down that they weren't as effective for grinding, or maybe they just got indigestion every now and then.
Where did these rocks come from?
I don't know exactly. These, if they're truly gastroliths, they would have come from out in Utah or Wyoming.
How do we know that these weren't just polished by rubbing against each other in a stream?
Well, that's controversial too. Some people think that, have argued that most of the gastrolith stones that are found are just polished stream pebbles. If you find polished stones like this in a rock that wasn't deposited in a stream, then it's kind of difficult to argue that they're stream pebbles. They're also very highly polished. They look like they've been through a rock tumbler. And stream stones that I've seen don't, to me, look quite as polished as these.
It's quite a feeling to hold something in your hand that was inside the stomach of a dinosaur.
Yeah, some people would be grossed out by it, I guess, but I think it's fascinating.
Well, we don't have any dinosaur coprolites around.
I don't have any, but there are some.
Yeah, they sell for a lot of money, the fossilized remains of dinosaur droppings.
Oh, yeah. Anything associated with dinosaurs, I'm sure, sells for a lot of money. There is somewhere out there, I don't know her name, but I remember seeing an article about her. There is a graduate student who is diligently assembling all of the available dinosaur coprolites to try and make some sense out of them and maybe learn something about the digestive habits of dinosaurs from them.
Let's take a look. I still want to talk about the other groups of dinosaurs, but I'm getting into some of the fossils now. What is this?
Okay, this is my best example of a dinosaur bone that I was able to scare up in the geology department at Hofstra.
And how do we know it's a bone? It looks like it has some kind of structure here.
Yeah, let me heft it for a second. Just hold it up.
Slowly.
It has the general morphology of a bone. If we turn it this way, you can see that there's sort of a smooth shaft. It's obviously been broken at the bottom here.
And this would be the head of the bone.
Yeah, this is some
neck.
kind of articulating surface here, and I'm not
Like
sure
a
exactly.
Femur or
a femur or a shoulder
arm bone, shoulder bone,
a collarbone. So the articulating surface, the shaft, and since I don't have the whole bone, I'm not quite sure what bone it is.
And you can see the sponginess that looks. I'm a vegetarian, but I used to eat meat. This looks like the inside of a chicken bone right here.
Yeah, when you, I mean, that's sort of in the field. One of the ways you know when you found bone is that fossilized bone has a very spongy look to it.
Yeah, this is not.
The spaces are filled in with mineral very often, so it's not truly spongy, but you can see all the little intersecting, crisscrossing bone spaces.
So when you have a fossil, for people who don't know it, the bone gets replaced molecule by molecule by minerals that sort of dissolve in the water and then get deposited, so that it's sort of like a mold of the bone that's accurate down to microscopic detail.
There's actually a whole range of ways to preserve bone. In some cases, you do get the complete replacement of the bone with mineral, like you said. In other cases, most of the organic or all of the organic material in the bone is removed. The bone mineral is left behind, and then the spaces where the organic material was get filled in by mineral. And in some very rare cases, you can even get the organic material preserved. And there's a great rush on right now to try and extract DNA from dinosaur bone, and the samples of dinosaur bone they're using are samples where there does seem to be some organic material preserved.
And have they been able to get any DNA? And
a couple of
use what is it, polymerase chain reaction to
PCR,
replicate it like in Jurassic Park?
A couple of labs have gotten DNA from their bone. The question is it really dinosaur DNA? If you want to play the DNA game, what you have to do is you have to get yourself some of this very rare, wonderfully preserved bone.
How many ounces of that are there in the world?
I don't know, to tell you the truth. I'm not sure. But you have to then digest. You have to get a sample of that pristine or not pristine, but well-preserved bone. Digest it with some enzymes to get out whatever organic material is there, and then try and isolate from whatever organic material is there the actual DNA. Then you take the DNA and you put it in your polymerase chain reaction and multiply it. Essentially, make
it's like a molecular photocopy machine.
Right. You just sit there and photocopy your DNA until you have enough to actually work with. And then
what have we gotten so far?
Well, you go through all this work and you end up with some DNA, but then you have to try and figure out, is it really dinosaur DNA? So what you do is you take the DNA that you've gotten from this, and you first compare it to human DNA to see if some of your skin cells got into the mixture.
Mm-hmm.
And what you've done is isolate your own DNA. If it's not human DNA, then you compare it to a whole bunch of different common funguses and bacteria that might have been present in the room where you were doing the analysis, and try and show that your DNA is not fungal DNA and not bacterial DNA. If you can do that, if you can eliminate the possibility that it's fungal or bacterial contamination, then you take your DNA and you compare it to crocodile DNA and you compare it to bird DNA, because crocodiles and birds are the closest living relatives to the dinosaurs. And if you can show that it's very similar to crocodile and bird DNA, and you can convince people that you haven't had any crocodiles or birds running around in the laboratory in the last couple of months, then you can publish and say, all right, I've probably got some dinosaur DNA. Nobody has gotten that far yet.
How far have they gotten?
I suspect they've gotten up to the stage of, I've got some DNA and I'm still trying to prove it's dinosaur DNA, because you have to compare it to a lot of different types of DNA.
How long have they been doing this?
Good question. A couple of years, I think.
Oh, that's very recent.
Yeah, it hasn't been going on for very long.
A couple of decades, and as some of the techniques evolve and get better, maybe we'll get somewhere with that.
Yeah, I'm sure it won't be long before we read in the newspaper that somebody has convincingly and confidently isolated some dinosaur DNA.
Okay, but these would be fragments, so we couldn't actually reconstruct a dinosaur the way
No.
they can in
We don't.
Jurassic Park anywhere within the next few centuries.
I mean, if I gave you a vial of perfectly good, freshly extracted lizard DNA, you couldn't make a lizard out of it. The technology to do that just doesn't exist. What people are very interested in getting, the reason that scientists want to get dinosaur DNA is that if they can get DNA from different kinds of dinosaurs, then they may be able to compare the DNA fragments that they have to these other fragments and try and learn something about the genealogy of the dinosaurs themselves. So that's why people are interested in dinosaur DNA for the most part, not for Jurassic Park and reconstructing living dinosaurs. That's science fiction.
Right, at this point.
Yeah, and will be, I think, for a long time.
Yes. Okay, let's look at some of the other fossils. We don't have all that much time left, and then we'll go into the other groups. You've got something that is not a dinosaur.
Okay, well, let's just polish off the other groups,
okay.
And then we'll talk a little bit about dinosaur extinction. I think that would be a good way to end up the show.
Okay.
We can go out.
Oh, very briefly. This is so beautiful.
All right, yeah.
You just...
Okay, sure.
Okay, this is an amniot. It's like an octopus in a shell. Octopuses are mollusks, like clams and oysters. And I've never held one of these in my hands before. They went extinct with the dinosaurs, and this is the shell. And you told me before the show that this one is fairly narrow because these things swam and were aggressive.
Yeah, these animals they're similar to the pearly nautilus. They're called ammonites, and the ammonites during the age of the dinosaurs were some of the most abundant animals in the oceans, and there were many different kinds doing many different types of ecological or living different types of lives in the oceans. Towards the end of the age of the dinosaurs, some of them got very large, and this is a relatively small example of this particular kind of ammonite. I've seen them
like that.
Okay,
and we've got some fossil oysters that don't open with two equal halves, that actually have a little covering.
Oysters, during the age of the dinosaurs, were doing strange things. Instead of being flat and gluing themselves to the seafloor, they were becoming very sort of bulbous and round and hunkering down in the mud. And one half of the oyster shell would become very bowl-like, and the other half would then form a little lid kind of on the top.
This is really cool, and this is beautifully preserved.
And I dug that up in northern New Jersey.
Okay, and how about this?
This is a very strange animal. Believe it or not, let's turn it around this way.
Okay.
Go ahead. That's a clam. A particular group of clams towards the end of the age of the dinosaurs decided that they were not content being clams anymore, and they wanted to be coral reefs. So these clams developed one of their shells into a long, cemented, stable sort of home to live in, and the other shell then became kind of a lid on this. And down in the Caribbean region, you had huge reefs that were formed almost entirely out of these very peculiar clams. These are called rudistids.
These also went extinct at the end of the Mesozoic.
Right.
And we've got another dinosaur fossil here, and we have a replica of a dinosaur egg. This is egg substitute, no cholesterol.
Right.
And what is this?
Okay, this is the tailbone of one of the other groups of dinosaurs we haven't talked about. The other dinosaurs, the bird-hip dinosaurs, were all plant eaters, and generally you had a group that was heavily armored, the group that had long horns, the ceratopsians, and then a group of bipedal animals, which were sort of the cattle and the and the gazelles and the antelopes and deer of the dinosaurs.
So they just ate a lot of plant material, reproduced quickly, and ran like hell.
Probably ran around in herds. And this is the tailbone from a late dinosaur age example of one of these herbivorous dinosaurs, a hadrosaur. Some people call them duck-billed dinosaurs. This came from South Dakota, and I found it myself. I was at a dinosaur quarry in South Dakota, and if you're in the right place, people think dinosaur bones are rare, and overall they are, but if you're in the right place where there are dinosaur-age rocks with dinosaur bones in them, they're everywhere. I mean, you wander around, and there are pieces of dinosaur bone eroding out all over the floor.
Should people go and collect them for their own curiosity, or is that destroying historical treasures, or are they all going to be destroyed by weathering and there's more below them anyway?
My philosophy on fossil collecting is that if you're collecting material that's just sort of lying around on the ground, and bits and pieces of dinosaur bone. There's nothing wrong with that.
Hmm.
If you're going in with a backhoe and extracting beautiful fossils for sale, I have a little trouble with that.
Hmm.
If they're specimens of animals that have been very well described by paleontologists and aren't of great scientific interest, then it's not a big deal. But the danger is that that unique specimens will not ever be seen by paleontologists
Right.
that have nevertheless come to light.
Okay, let's go into our theropods. We've got a T-Rex and an Allosaurus.
Mm-hmm.
Ah, great.
Very good. Very
Okay.
good.
And tell us a little bit about them. Why does the Allosaurus have longer arms than the T-Rex? Why does the T-Rex have such short little arms? And without arms, how did it kill things?
Well, that's a good question. And let's start. The Allosaurus is sort of typical of most of the animals in this group of dinosaurs, the theropods. It's obviously a predator. It has lots of sharp teeth in its jaw and sharp claws, very strong arms for grabbing its prey, or at least holding onto its prey once it captured it. And there were many, many different kinds of these predatory dinosaurs, some very large, some very small, that had many, many different ecological roles.
Do we know if they were solitary or if they were in packs like some modern predators?
Well, there's some evidence to suggest that that some, especially the smaller ones, might have hunted in packs. There's the Velociraptor of Jurassic Park, which is really an animal called Deinonychus, which has been found out in the West,
with the huge claws
on
its feet,
on its hind legs. When all specimens of Deinonychus that have ever been found have been found associated with the skeleton of one species of large herbivorous dinosaur, and they always find evidence for more than one Deinonychus. So it really looks like these animals were feeding on this one type of animal, and they were feeding in groups.
Mm-hmm.
Tyrannosaurus was probably solitary, and he's been called the original land shark. That he didn't need long grasping arms because he had this huge head full of teeth, and he may have been kind of a sit and wait predator. He would have sort of remained hidden, and then if something got close enough to him, he would just sort of leap out and open up that big jaw and just chomp on whatever he was hunting. And then, like Komodo dragons, these big lizards that live out in Indonesia, he may have inflicted a bite and then let the animal bleed to death before he actually went in and
which
started
sharks
eating.
do too.
Sharks do that too, yeah. Mm-hmm.
Okay, yeah, it's the modern mammals that will go for the throat, like the cats and the dogs.
Right, the cats and some of the large cats like to suffocate their prey. Essentially,
Mm-hmm.
they bite the throat and prevent the animals from breathing.
Right.
It's unlikely that these meat-eating dinosaurs hunted that way.
Okay, now let's get into the extinction, since we only have about 8 minutes left.
Okay.
The popular theory now is, of course, that the dinosaurs were destroyed by an asteroid or comet that hit the Earth, and that this landed somewhere off the Yucatan Peninsula. How clear is that, and what other factors are there that were possibly making this a little less clear?
Well, this is the biggest debate in paleontology today. And
for a good 15, 20 years, right?
Well, it's...
When did the Alvarez's first start with the theory of the comet?
I guess about 10 years ago, I think.
Only 10?
Yeah, it wasn't that long ago. And it's amazing how polarized this debate has become. I can show you articles from very reputable scientific publications, and you read one article and you're absolutely convinced that the asteroid struck and it caused the death of the dinosaurs. You read the other article and you're absolutely convinced in the other direction.
That's happened to me, just reading stuff in science magazines.
Yeah, it's hard to
well,
really
what are
sort
the
it out.
evidence pros? What's the evidence pro and con? Give us both sides, and maybe we can figure it out ourselves in 5 minutes.
Well, in 5 minutes. It all started when some researchers noticed that there seemed to be a thin layer of iridium-rich clay in certain places, right at the boundary between the last dinosaur age rocks and the first non-dinosaur age rocks. And iridium is an element which is scarce in the crust of the Earth, but it's very abundant in asteroids and in meteorites and things. So this suggested to these researchers that a large asteroid or comet or something from outer space had impacted with the Earth and sort of exploded and raised a cloud of dust. And when that dust settled, it was full of iridium from the original impact.
And weren't there also a lot of spores of ferns right above that, which would be the first things to regenerate at that time after worldwide devastation?
Well, once they put forward this proposal and said, okay, we have this iridium layer, we find it in Italy, we can find it in Western North America, we find it in other places, it seems to be a global feature. We can explain the iridium by an asteroid or a comet impact. Then other people started looking for maybe other evidences for some sort of catastrophic impact. And there have been a whole bunch of different ones. What you're referring to is called the fern spike in certain localities in western United States and western Canada. Above the last dinosaur age rocks, they find lots and lots of fern spores, as if the normal flora had been wiped out and then the opportunistic ferns had come in and grown for a while before the normal flora then came back. Other people would argue, though, that there was a climate change and things got a little wetter and the ferns came in. So it's not equivocal, it's not conclusive evidence.
Okay, and what is the evidence against the impact?
Well, no crater yet. And the Yucatan crater is still, I think, up for debate because
is the rock around there? Does it look like something in the vicinity of a crater, or is it some other geological formation?
From the surface, you can't see. If there is a crater there, it's buried. So we have to rely on remote sensing geophysical techniques, which suggest that there's something like a crater down there. But there are other explanations, like it might be a body of igneous rock. And there are people who claim to have seen drill cores, actual samples from where the crater is, that suggest that there's no crater there. So until I think we
what
drill
happened
some
to
holes,
the drill cores?
They were lost in a warehouse fire.
Mm-hmm. Wow, that's really unfortunate.
I mean, I don't want to say that there isn't a crater there, because there might be, but I think until somebody raises some money to go out there and drill down right where the crater is supposed to be and actually see what the rocks are that are down there and see if they're all jumbled up and they look like they've been smashed by an asteroid, we're not going to know for sure. So that I like to think that the crater issue is still open.
What about the shocked quartz? There's a mineral, a variety of quartz that you only get with impacts, and I've read that people have found that around that area, which would be very indicative, almost like a smoking gun.
Researchers have looked for these tiny grains of quartz that have evidence of having been compressed, been shocked by an impact.
How much of that has been found?
Well, there's shock quartz in this Cretaceous Tertiary, this final little thin layer with the iridium in it, all over the world. But
is there more of it near the impact or the supposed impact? Or we just haven't drilled down?
I'm not sure. I'm not sure how that's been worked out. But there are people who argue, though, that you can get shock quartz from volcanic eruptions too. So that line of evidence is still being debated.
And what evidence is there that it was something else that made the dinosaurs extinct?
Well, the other evidence is simply that even if there was an impact, it doesn't. You can't prove that just because there was an impact that's why the dinosaurs went extinct. And also the pattern, the different types of animals that went extinct with the dinosaurs don't necessarily seem to be the ones you would have expected from an impact. Well,
you'd expect the larger animals to go extinct first, and the smaller ones that can reproduce faster and don't need as much food, like the mammals, to have been able to survive something like this a little better.
You can argue it several different ways. Well, some mammals made it through, some went extinct. Small reptile, lizards and snakes didn't seem to have been too much affected. Turtles weren't affected. People are still looking at the pattern of the extinctions and trying to come up with a consistent theme, with sort of a fingerprint of what might have been the mechanism that was causing the extinction. So,
okay, well, we're going to get to the bottom of it. No, we can't. We've run out of time. Too
Right.
bad. We're just about to solve the extinction of the dinosaurs, but our time is up. I'm naturalist wildman Steve Brill. This has been Foraging with a Wildman. My special guest is Brett Bennington, paleontologist at Hofstra University. Thank you very much. We will continue this with more fossils on another show.
Great.
See you in the field.